Hello, everyone. I figured I would start doing problem sessions for each section, just to help you guys see how to solve these problems in practice. The lectures, maybe it's a lot of theory and a lot of building up the tools on how to solve these problems. And then I figured I'd do problem sessions where I just go through and solve the problems and solve several of them, and you guys can see how it's done in practice. So let's give that a try. So let's start with some easy comparison test problems. We want to use the comparison test to determine if certain series converge or not. We're going to use comparison test and limit comparison test. So let's start with this series. These problems are going to mostly come from the book. All right, so let's look at this series where each of the terms is 1 over n cubed plus 8 from 1 to infinity. We're adding up all these terms. This is our series. So I want to use comparison tests to determine whether this converges or not. All right, so what do I compare it to? Again, I'm trying to, like I said in the lecture, find the simplest form of this. So if I'm looking at this, these terms, I would have just 1 over n cubed, right? So that's telling me I should compare this to 1 over n cubed. Okay, now let's look at this series. Okay, this converges by p-test. So that's giving me a hint that this is probably going to converge, but I need to go through my steps, right? Okay, one, verify all terms positive. Again, these first two steps are usually pretty simple. All right, is 1 over n cubed plus 8 always positive? Remember, for n, what are we plugging in? We're plugging in natural numbers, so 1, 2, 3, 4, etc. So if we plug in natural numbers, is this going to be positive? Yeah, it's always going to be positive. Same thing over here, 1 over n cubed. If we're plugging in n's, that's always positive. Okay, what is my next step? I want to show my inequality. Okay. So, what inequality do I need? I need 1 over n cubed plus 8 is less than or equal to 1 over n cubed. Is this true? Let's see. On the left side, I'm dividing by a larger number, so this fraction should be smaller. Okay, so we could say this inequality holds for n greater than or equal to 1. Okay. Final step, we summarize. Okay. We're saying this converges. Why does it converge? By p-test. Then our original series converges by comparison test. Okay, so that would be how we do that problem methodically step by step. Okay, so again, we're starting with this series here, 1 over n cubed plus 8. We're comparing it to this series, 1 over n cubed. We need to check that all terms are positive. Okay, we checked that. We checked that this inequality holds for all n. Again, it doesn't have to be anything too involved to verify these first two conditions, but we do need a mixture, okay? And this second condition in particular is we have to be careful with, because remember what I said in the lecture, that sometimes this inequality won't hold. It'll be going the wrong way. And then that tells us we need to use a limit comparison test, not comparison test. So this second step is very important. And then once we have these two conditions, we can conclude by comparison test our series converges. All right, let's see another problem. How about let's start our series at 2 this time and have the series 1 over square root of n minus 1. So why am I starting at 2? If I had started at 1, I'd have 1 over 1 minus 1, so 1 over 0, that's undefined. So I'm starting the series at 2 just to make sure everything's defined, okay? Now, I want to figure out if this series converges or diverges. All right, so this is section 11.4, so I kind of automatically know I want to use comparison test. But even if this wasn't in section 11.4, I need to be able to see that this is a comparison test problem, especially for the test in the final. You're going to be given a series and you're going to ask whether it converges or diverges, but you're not going to be given any clues as to what test to use or what section the material is coming from. So we need to be able to spot that this is a comparison. So when I see this, I see immediately that this is very close to the series 1 over square root of n, okay? So let's see. Let's keep track of that. I want to compare this to this series, all right? And we'll start that at 2 as well. Now, what's going on with this series? I can write this as 1 over n to the 1/2, okay? Does this series converge or diverge? Well, again, this is a p-test, right? P-test is going to come up a lot with comparison test. It's going to be used in conjunction with comparison test, okay? So this series diverges by p-test. All right, so does that tell us this? What does that tell us about this? Well, maybe that's going to tell us this converges, but we need to have our inequality going the correct direction. Okay. So 1, verify all positive. Boom. Okay, is this always positive when n is greater than or equal to 2? Let's see, if I plug in 2, I would get 1 over square root of 2 minus 1. Well, square root of 2 is a bit bigger than 1. It's what? It's 1.4, something like that. All right, so this should be positive. And what about when I plug in 2 over here? I have 1 over square root of 2. Again, that's positive. Okay, so everything's positive. 2. What's the inequality? Well, let's see. I'll write my terms down. Okay, what's bigger? Again, my little number dyslexia is coming in. I confuse 2's and n's a lot. Okay, so which way is my inequality going? Okay, which is, let's see, what's going on? So if I can't see it immediately, instead of looking at the fraction, I'll come over here and I'll look at these two first. Again. Okay, so let's look at this first. Which is bigger, this term or this term? Well, let's see. I have square root of n on both sides, and then I'm subtracting 1 from this left side. So let's see. This left should be smaller than right. Okay, what happens when I turn these into fractions? Okay, over here, since square root of n minus 1 is less than square root of n, I'm dividing by a smaller number over here. So my fraction should be larger. So the inequality is going the other direction now. So this is my inequality. Okay, what does that tell us? All right, I have this series. We say this one diverges. And then this series should be bigger than that, right? So does that meet one of my my conditions, or does that meet the criteria for the comparison test? Yes. So my original series diverges. So to sum up, I would say 1 over square root of n diverges by p-test. So diverges by comparison test. All right. We've seen stuff mostly, even in the lecture, the stuff we were simplifying was mostly in the denominator. So in this problem, I simplified this denominator into this, and that was my comparison. Okay, but maybe this stuff's going to be in the numerator as well, or both. So let's see an example of that. Let's try this problem. Okay. So again, I want to use comparison test. And what should I compare this to? Again, I need to look for the simplest version of this series. Okay, so focus on this n over n cubed. What would that give me? Actually, so if I focus on that n over n cubed, let's just write that over here. Well, that is equal to 1 over n squared. Now this, again, converges by p-test. We're seeing p-test again, okay? So maybe that's a hint that this should converge as well. Okay, so let's go through our steps. 1, verify all positive. All right, is this always positive? Let's see, if I plug in 1, I'd have 0. Let's see, so it's not positive, it's greater than or equal to 0 though, that's good enough. As long as it's not negative, we're good, okay? So positive, you could say it's non-negative for n greater than or equal to 1. What about over here? If I plug in n equals 1, I'm starting at 1 over 1, and then let's see, if I plug in 2, 3, 4, etc. Okay, the terms are getting smaller, but they're all still positive. And then same thing over here. If I'm plugging in larger values of n, what's happening on the top? Let's see, this is going to be a positive number. This is going to be a positive number. So the fraction is going to be positive as well. So everything's positive. Okay. Let's see. Now what do we need? We need to find an inequality. We need to show that there's some inequality going on between n minus 1 over n cubed plus 1 and 1 over n squared. Okay. Maybe it's not clear how these two are related at first, but again, we can take this step by step. So let's see. Let's start with n minus 1 over n cubed plus 1. Well, let's see, we're subtracting a number on top, right? So that should be less than or equal to this, correct? And what's going on the bottom? Okay, we're dividing by a number slightly larger than n cubed. We're adding 1 to it. So that should be less than or equal to n over n cubed. And n over n cubed is equal to 1 over n squared. So to summarize, I have n minus 1 over n cubed plus 1 is less than or equal to 1 over n squared. And this is the inequality I want. Right? I have this series is convergent. So if all the terms of this series are less than or equal to, by comparison test, this should be convergent as well. Okay. So to conclude, I say 1 over n squared converges by p-test. So this converges by comparison test. Okay. We've been using p-test a lot, but it's not always going to be p-test. So let's see an example of a series that we don't use p-test in the comparison. How about this? 9 to the power n over 3 plus 10 to the power n. The idea with comparison test is that we want to compare our original series to something we can easily test for convergence or divergence, okay? So we were using p-test a lot because the p-test is pretty easy to apply, right? When I see powers of n, okay, if I can boil that down to a simple 1 over n to the power p, that's really easy to test for convergence, all right? So now I have 9 to the n over 3 plus 10 to the n. What should I compare this to, and what test should I use on the comparison? Well, again, I'm going to boil this down to its simplest form. That would be 9 to the n over 10 to the n, right? Okay, which I could write as this. 9 over 10 to the power n. Now maybe this is clear. This is a geometric series. And let's see, our ratio, our r term is 9 over 10. That's less than 1. So this is convergent by, we could call it geometric series test. Okay, now I need to go through the same steps for my comparison test. Okay, verify all positive, boom. Are these terms all positive? Yeah, if I'm plugging in n's, it doesn't actually matter what, if I plug in positive numbers, negative numbers for these n's, the n's are supposed to be natural numbers, so they should always be positive, you know, positive integers, 1, 2, 3, 4, etc. But really, it doesn't matter what number I plug in here. If I plug in if I have a power of 9, that's never going to be a negative number, right? It's always going to be positive. Same thing for this. Okay, so I got a positive number up top, I got a positive number on the bottom, so this term is always going to be positive. Same over here. I have 9 to the n, it's an n, not a 9. And I got 10 to the power n. So this is always positive. Okay, so everything's positive. My inequality. Okay, let's see. I would like this term to be less than or equal to this term to show it's convergent. So let's see if that holds. Okay. Let's see, I'm divided, and let's see, I got 9 at the n over 10 to the n over here. Let's see, I'm dividing by a larger number over here. So yes, this should be less than or equal to this. And then finally, I write my conclusion. I would say This converges by geometric series test. So converges by comparison test. All right. So these examples have been fairly straightforward. Let's start looking at something a bit more difficult. How about something like this? Feel free to pause this video at any time, obviously, and try these problems on your own before I get to them. Okay, so now I'm using K's just because that's how they've written it in the book. It doesn't really matter what letter we use for our index here. It could be N, could be K. It's representing the same thing. These are always going to be natural numbers, whether the letters K, N, etc. All right. Usually the N is standard. K is very common as well. If you were writing a test, I wouldn't, get into any really obscure letter. I don't know, not obscure, but I wouldn't go too far beyond N or K or anything like that. That's just a style thing. It's not wrong, but it would just be weird. All right. So this is a bit stranger because now, okay, we were dealing with usually n's or k's, polynomials of them, maybe geometric series stuff. Now we got a sine squared. So it's the same principles, it just takes maybe a little bit more thought. Okay, I would like, let's see, if I compared this to something, let's see, what would happen if I ignored the sine squared for a second? Okay, then I would have k over 1 plus k cubed. Okay, let's kind of go step by step. K over 1 plus k cubed. Then can I simplify this at all? Well, maybe. Let's see, if I ignored the 1, I would end up with k over k cubed, which is equal to 1 over k squared. Now, what do I know about this? Again, convergent by p-test. All right, what does that tell me about this? Well, maybe that means this is convergent as well. So let's use the comparison test to figure that out. Okay, is everything positive? Let's see. I need to verify all positive. So what am I using here? I'm comparing this series with this series. Okay, is everything positive in this series? Well, let's see. I have sine, but it's sine squared. So even if sine is like -1/2, I'm squaring it, and that's going to give me a positive number. So this sine squared is always positive. K is always positive. The denominator is always positive. Okay, so this one's always positive. What about this one? Is that always positive? Yeah, if I'm plugging in natural numbers, that's always going to be positive. And then what about my inequality? Is there some inequality going between these two? I'm comparing these two. To show that this is convergent, this series is convergent, I need this inequality. Is that true? Let's see. Sine squared. What do I know about sine squared? Sine squared is always less than or equal to 1. Okay. So this whole thing, I know I know that's less than or equal to k times 1, which is just k, over 1 plus k cubed. And now, how did these two relate? Well, I'm dividing by, let's see, I'll add this step in here, k over k cubed. Okay, I'm dividing by a larger number over here, so this should be less than or equal to k over k cubed. And then this is equal to 1 over k squared. Okay. So to conclude my inequality, I have k sine squared k over 1 plus k cubed is less than or equal to 1 over k squared. Okay. So my inequality is going the right direction. 3, I summarize everything. I say 1 over k squared convergent by p-test. So k sine squared k over 1 plus k cubed convergent by comparison test. Okay, let's continue looking at some more challenging problems from this section. Let's look at this. Okay, so this is a weird problem. I got cube root of k up top, and then on the bottom, I got square root of k cubed plus 4k plus 3. All right, so again, comparison test. What could I possibly compare this to? Well, let's see how we can simplify this. First of all, let's rewrite the top as cube root of k is k to the 1/3, right? Okay, let's see. Now let's look at this denominator. I have k cubed plus 4k plus 3. I'm taking the square root of all that. So really what's important here, I should always think that the highest power of stuff is going to be the most important in my numerator and denominator. So what's the most important here? It's this k cubed, and then I'm taking the square root of that. So how about we consider square root of k cubed, which we could write as k to the 3/2. All right, so I got k to the 1/3 over k to the 3/2. That's equal to k to the 1/3 minus 3/2, right? When I divide by an exponent, I subtract the exponent. Or excuse me, when I divide by a term with same base, different exponent, I subtract the exponents. All right. So let's see, 1/3 minus 3/2. So what is that? All right, if my mental math is correct, that should be k to the negative 7/6. Let's see, let me double check that. Yes, that is correct. Okay, so maybe I should compare this to the series. Let's see, k to the negative 7/6 is the same as 1 over k to the 7/6, right? So let's try comparing our original series to this. Now, does this series converge or diverge? Well, I got 1 over k to a power, p, okay? And let's see, this p is greater than 1, so this is convergent by p-test. Okay, So now let's go through my steps. Try and squeeze them in over here. Let's verify all positive. Okay. Is everything positive here? Yeah, when I'm plugging in positive numbers, the cube root and the square root of positive numbers are still positive, so this is positive. Same thing over here. Okay, I'm taking a power of a positive number. That's still going to be positive, so this fraction should be positive. All right, we're all good. 2. Inequality. I need an inequality. So let's write this again in this form. The inequality, maybe you're intimidated by all these terms, but the logic is the exact same. Okay, let's compare this to, this is the same as these two are equal, right? So let's compare this to this. All right, I got k to the 1/3 on top, so the tops are the same. Okay, and then on the bottom of this one, I got k to the 3/2. So what's bigger, this or this? Let's just look at the denominators for a second. This denominator, okay, k to the 3/2, let's see. This is, if I just had square root of k cubed, that'd be k to the 3/2, right? But I'm adding stuff to this. So this denominator is greater than this denominator. So that means when I divide, okay, I'm dividing by a bigger number over here. So this fraction should be smaller than that fraction. So this is the inequality. And that's what I need for comparison test, right? I know this is convergent. I want to show this is convergent. So I need the inequality going this way. Okay. So that is good. 3. So I conclude 1 over k to the 7/6 convergent by p test. And I'll say, so I'll just say original series converges by comparison test. Okay, I'll do a couple more regular comparison tests just very quickly. I'm not gonna write through them as slowly as I've done these so far, just to give you an idea of the logic. I'm not gonna write out the steps every time. So how about we'll look at a couple things that look simple, but maybe are a bit difficult. How about 1 over n to the power n? So this is weird, right? Instead of having n squared or n cubed, I have 1 over n to the power n. So the base is changing at every step, and so is this power. So this would be like adding up 1 over 1 to the power 1 plus 1 over 2 to the power 2 plus 1 over 3 to the power 3, forever. Okay, so that's a little confusing. Let's see. How about, let's look at these term by term. Let's focus on the stuff to the right of this line. Okay, so 1 over 2 squared, 1 over 3 cubed. The idea that I have for this is, my intuition here is that 2 squared is less than 3 cubed. So this term is less than this term is less, this fraction is less than 1 over 2 squared. And really, and actually, there's a better way to say this. Instead of 2 squared, let's say 2 cubed. Okay, so 1 over 2 cubed is less than 1 over 3 cubed. So this fraction here is sorry, I had a little lapse in my thought process. Okay, so I have 3 cubed is greater than 2 cubed, which means 1 over 2 cubed is greater than 1 over 3 cubed. Okay, so let's see. And then the same thing holds for the subsequent terms. So I can say that this series is going to be less than 1 over 1, and I got my little dividing line here. My original series is going to be less than or equal to 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4th, etc. Okay, and then what is that series? Well, if I wanted to write this in a compact form, this is 1 over 2 to the power n. And this is convergent by geometric series, right? So this is convergent. This series is less than or equal to that, so my original series is convergent as well. Similar logic, let's say for one over n factorial. So remember what factorial is. Factorial is, if I have 4 factorial, for instance, that's 4 times 3 times 2 times 1. That's going to be very important in this chapter, especially in future sections. So get used to factorial. Okay, so what do the terms of this series look like? I got 1 plus 2 plus, 1 over 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 plus 1 over 120. So let's see, can I find something to compare these terms to? Maybe just by looking at this, I can see that these terms are larger than the powers of 2 as well, these denominators. So this is, I could say this is less than 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16, etc. So that's the intuition. We would maybe need to be a bit more rigorous in showing that. And how could we do that? We could say, I want to show, what do I need to show? I need to show n factorial is greater than or equal to 2 to the n. That'll tell me that 1 over 2 to the n is greater than or equal to 1 over n factorial. Okay, let's see. We could do this by something called induction. That's a bit maybe too complicated for you guys, but let's see. It holds for the first step, right? It holds for when n is equal to 2, it's true. Boom. What about at the next step? Okay, n equals 3. Let's see, is 2 cubed less than, and actually this should be 2 minus 1. Is that true? Yeah, well, this is 2 squared, which is 4. This is 6. Boom. Okay. And then the induction means we're just, we have a clever way of checking at every step. We check at a first step, and then we show it's true for every following step. Let's not go into that. If you can see the intuition from here, that's good enough. Being able to spot this is, takes a bit more comfort with these comparison tests. So we got to develop that. All right, let's try some limit comparison test problems. So remember, limit comparison test is good when we can't see which direction the inequality is going. So let's try this problem. I think this will give us a nice limit comparison test. How about n plus 2 over n plus 1 cubed, starting at n equals 3. Okay, so let's see, what could we try and compare this to? Okay, if I multiply all this out, I would get n cubed plus blah, 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 right? And then on top I have n. So let's try and compare this to n over n cubed, which is equal to 1 over n squared. All right. So 1, verify all positive. Okay, so positive. That's going to hold. Boom. 2. Here's where we run into problems. Checking the inequality. Okay. I want to show, and since these two are equivalent, let's work with this one. What inequality do I have going here? Well, let's see. On the one hand, this numerator is bigger, right? So I'm tempted to say that this is bigger than that. But on the other hand, this denominator is bigger, so that makes me think maybe it's this. So now it's not just that the inequality is going the wrong way, it's just that I don't know really what's going on with the inequality. I can't tell if it's bigger or smaller. What's going to happen in the long run when n gets really big? So now it's not just that the inequality is going the wrong way, it's we don't even know what's going on with the inequality. This is another good time to use limit comparison test. Okay. So I switched to limit comparison test. Okay, so remember I'm doing an over bn, and it doesn't matter which is an and which is bn. I'm going to take, I'll say this is my an and this is my bn. I want to look at the limit of an over bn. Okay, so limit as n goes to infinity. So I want to look at the limit of n plus 2 over n plus 1 cubed over 1 over n squared, which is equivalent to n over n cubed. Same thing. I could use either one of these in my limit comparison test. Just for simplicity, I'll use this one. Okay. So just rewriting, I want limit n plus 1 over, what was it? N plus 2. Over n plus 1 cubed. And then I'm dividing by 1 over n squared, which is the same as multiplying by n squared over 1. Okay. That gives me n cubed plus 2n squared over n plus 1 cubed. Now, what is this limit? Okay, if I multiply this out, like I said before, I'm going to get n cubed plus blah, blah, blah. I'm not even going to bother multiplying this out because I know what the first term is. The highest power of n is going to be n cubed. So if I have limit of n cubed plus some stuff over n cubed plus some stuff, and these two terms, the highest powers of n are both less than 3. So these are the highest powers of n. What do I know about the limit of this? Really, the limit is determined by these first two terms, right? The coefficients. So we have the limit equals 1. Okay, what does limit comparison test say? Okay, if the limit of an over bn is a number greater than 0 and less than infinity, then the two series do the same thing. Okay, so from my limit comparison test, I know my original series, boom, and this series do the same thing. I know this series converges by p-test, so that means this series converges. Okay? So how would I write out this one? Let's just start from scratch. Limit n plus 2 over n plus 1 cubed. This shouldn't be limit, this should be a series. So I'm doing this series. We started at 3. Okay, so 1, verify all positive. Again, that's good. And I know, let's see, at this stage, I know I'm gonna do a limit comparison test with 1 over n squared. Find limit an over bn. Okay, we said that was equal to 1. So 1 over n squared converges by p-test. So original series converges by limit comparison test. With that, this last example, I'll do maybe one more example of limit comparison test. How about this series here? Okay, so again, this is going to be one that we can't do by straight comparison tests. Okay, let's skip this. Let's try it and skip to step 2, the inequality. Let's see, what should I compare it to? When n gets big, these are going to be the dominating terms. So let's try and compare this to, okay, if I had this in the form of a series, this would be divergent by geometric series test. This ratio is greater than 1, so this is going to diverge. All right, so I would like this term to be greater than or equal to that, okay? And this, since I'm adding n on the top, that suggests, yeah, maybe this is greater than or equal to. But then when I'm looking at the bottom, well, this denominator is bigger, so I'm dividing by a larger number on the left. So that makes me think, okay, well, maybe it's this. So again, I'm not sure what the inequality is, which way the inequality is going to go. So this is telling me I should use limit comparison test. So I use this as my AN, this is my BN. Let's see what we get. Okay. So let's try limit comparison test. So I divide, let's say this is my AN, this is my BN. I divide my AN by my BN. Let's go ahead and go to a new page. So I'm dividing, so that means multiplying by the reciprocal. And my result is now, what is the limit of this? Well, maybe that's really complicated to think about the limit. I could break this into pieces. I could say this is to the n over n. And then ask myself, okay, what's the limits of these individual pieces? And I'm missing an n here. Okay, looking at these, maybe it's not clear what the limit is still, but let's see, the limit of this, this is going to be the dominating term here, 2 to the n over n, 2 to the n times n over 3 to the n times n. So the limit of that piece should be 2/3. And then what's the limit here? Okay, we have 6 to the n, and then this is going to dominate. So that should be 0. Okay, let's see, could we double check that? Yeah, we could divide out the 2 to the n here. Okay. Okay. So this piece is equal to n over 3 over 2 Okay, so now I have this. This should be the same as this. What's the limit of this? Limit of that is 2/3. Okay. And what about the other piece? The other piece was 6 to the n over 3 to the n times n plus 6 to the n. Divide out the, let's divide out a 3 to the n from both top and bottom. I would get 2n plus 2. Okay. Limit of this is 0. Okay. So the limit of our an over bn is equal to 2/3. So that means these series are going to do the same thing. They're either both going to converge or both diverge. I know this diverges, so that means my original diverges. We probably could have done this an easier way by looking at our original. Instead of trying to do any comparison test, just do divergence test. Okay, so recall divergence test. I look at the limit inside. If that limit doesn't go to 0, the series has to diverge. So I could have maybe evaluated this limit and said, okay, it looks like this limit's going to go to 3/2, and then that tells me that the limit's not going to 0, so this has to diverge. All right, I'll end the video, the problem video there. I'll be online tonight, Thursday, 6 to 9, for virtual office hours.